Scientific revolution. The term scientific revolution indicates the historical period in which modern methods of scientific inquiry were established. Although this revolution took place over hundreds of years, it is usually associated with the great discoveries of the first modern scientists, including Johannes Kepler, Nicholas Copernicus, Galileo, and Isaac Newton during the 1600s. The most enduring legacy of that era was the formulation of the scientific method, a strict set of rules that dictate the proper course of establishing facts. The method involves the formulation of a hypothesis, the listing of assumptions, the isolating of variables in any experiment, and the rational analysis of experimentally observed data to support a conclusion. Before the scientific revolution, scientists did not act within those guidelines. Thus, their conclusions were based on confusing arrays of mixed variables and the acceptance of false assumptions about the world that stemmed from the beliefs of their eras. Therefore, the scientific revolution had as much to do with the shift away from religious beliefs as it did with formal scientific and mathematical advances. Science before the 17th century. The state of science prior to the scientific revolution was a mixture of three unrelated influences: the scholarly writings of ancient Greek philosophers such as Aristotle, technological advances made by the tradespeople of the Middle Ages, and the imposed doctrines of whatever religious sect was in power at that time. Although work was being done in the fields of biology and chemistry, the main thrust of the scientific revolution was centered around astronomy and physics. However, the astronomy of antiquity could never meet today's standards. Using geometry, a complex web of over 80 circles was constructed to explain the paths of the sun, moon, and planets. But the system's complexity was a direct result of the false assumption that the Earth was the center of the universe. Nonetheless, the main principles of the natural philosophers of ancient Greece were generally accepted in one form or another for the next 1400 years. Revolution begins. Polish astronomer Nicholas Copernicus fired the first shot in the scientific revolution at the turn of the 16th century with his development of the heliocentric theory. He realized that complicated older solar system models could be improved by placing the sun at the center of the universe and having the Earth and planets revolve around it. Copernicus's central idea was to have far-reaching consequences. Putting the sun at the center of the universe upset the fragile hierarchy between heaven and earth that was ingrained in Catholic Church doctrine. Thus, supporters of Copernicus's ideas were persecuted by the Church until the mid-1600s, when those ideas became widely accepted. The modern view of the solar system was developed at the turn of the 17th century by Scandinavian astronomer Tycho Brahe and his German disciple Johannes Kepler. Copernicus's model represented a major step forward in the understanding of the universe, but inconsistencies remained. Copernicus's supporters believed that the planets were embedded in transparent crystalline spheres whose rotations around the sun accounted for their circular motions. Brahe overturned that belief when he observed a comet that passed through the solar system without shattering the supposed spheres. Brahe was unsurpassed in his observations and measurements of the night sky, and they were so accurate that they pointed to inconsistencies in the calculations of Copernicus's model. Brahe's work led Kepler to drop the assumption of perfect circular paths and propose that the planets moved in elliptical paths around the sun. From that idea, he derived his three laws of planetary motion. Thus, ancient Greek and church principles were replaced with immutable laws of nature and observational proof of their validity. At around the same time, the Italian Galileo was performing experiments related to the motion of objects. Galileo's genius lay in his ability to isolate the variables of his experiments, which created ideal conditions from which he deduced mathematical formulas. For example, in his experiments with balls rolling down inclined planes, he made sure that all the surfaces were polished smooth so that the motion of the ball itself could be studied. Galileo's work was important because his equations were verifiable by repeated experiment and could be applied to almost any situation. For instance, it was known by observation that a cannonball shot from a cannon would fly the farthest if the angle of the cannon was set at 45 degrees above horizontal. Galileo's equations showed why that was the case, but also that the cannonball would follow a parabolic path, and its time in flight could be calculated. Once again, mathematics and observation through experiments took precedence in the formulation of scientific facts. Philosophy and the scientific method. By the early 1600s, two schools of thought emerged about how proper science was to be accomplished: the inductive approach and the deductive approach. England's Francis Bacon, a proponent of the scientific method, emphasized the value of experimental research. Bacon's approach consisted of making lists of observations and extracting information based on all things considered. That approach, which came to be known as the inductive method, became indispensable to the biologists of the 19th century and would culminate in the work of Charles Darwin. The more important philosophy in the context of the scientific revolution was that of Francis René Descartes. Descartes championed the mathematical and deductive approach that was inherent in Galileo's discoveries. The dichotomy between the measurable and unmeasurable, the separation of mind and body, is a hallmark of Western thought, and largely exists to this day. Descartes' philosophy helped define the goals and methods of science by requiring the elimination of extraneous facts and beliefs. Newton and gravity. In the 17th century, the centers of scientific activity shifted from Italy and Germany to the more prosperous regions of France, the Netherlands, and England. The shift was good news for science, in that those countries were under the influence of the Protestants, who were much kinder to the development of new ideas than the Catholics had been. The Englishman Isaac Newton is credited as the most significant scientist of his time. Aside from developing the calculus, he is known for establishing the universal law of gravity, thus putting to rest the speculations and misconceptions of his predecessors. Newton did not discover gravity per se, but he did make the important connection between Galileo's work on falling objects and Kepler's laws of planetary motion. Using rigorous mathematical proofs, Newton showed that falling objects move under the same influence as the planets. That influence, of course, is gravity. Newton's laws of motion were accepted as uncontested laws of nature for 200 years until Albert Einstein proved him wrong with his special and general theories of relativity. While the scientific revolution represented an overall break with superstition and religious hegemony, it is important to note that beliefs still play a part in science. What scientists of one era believe to be fact may be disproven by scientists of the next. Einstein himself did not believe in the validity of quantum mechanics, a field in which he made significant contributions.